Thanks, Chris, for the introduction and for the opportunity to speak here at this great program. So today I'm going to be talking about a program which has been worked out over a series of papers with some wonderful co-authors, my advisor, Andy Sturgeon at King's, Sabine Harabey, a postdoc at Dias in Dublin, and Sam Bartlett-Tisdall, also a PhD student at King's. And the goal of the talk will be to be fairly broad rather than deep on any of the defects. The goal will be to try to cover the space of defects, see as far as we can what this looks like rather than focusing on any particular theory in great detail. You, of course, can do this, and for specific theories, I'll point out that people have focused on them, like the magnetic line defect in the Ising model, this ordinary surface in the ON model, and so on. Now, we're at a program for defects, so I won't try to introduce the general notion of a defect, but I will give you a picture about conformal defects specifically, because some of you may not be as familiar to carry with you as I speak. So the idea is we're going to start with some sort of conformal bulk, some CFT. And in this talk, we'll be working perturbatively. And so we can classify this based on some perturbative couplings, which will lie at the fixed point of some beta function. And we want to perturb this CFT by a particular extended operator. So we'll put some p-dimensional hyperplane. In principle, you can curve this, you can make it whatever surface you like, but for simplicity, we'll stick to just a flat hyperplane in p dimensions. And we want to add interactions localized to this submanifold. So there'll be some couplings H. And a conformal defect is constructed by allowing these couplings to undergo an RG flow towards the IR, where they will reach their own fixed point, H star, at which point the setup will be conformally invariant, not under the full d-dimensional conformal group, but instead under a p-dimensional conformal group. So the symmetry will be broken from the bulk conformal symmetry down to a remnant conformal symmetry on the defect times some group of transverse rotations, which from the point of view of the theory living on the defect just looks like an additional global symmetry. And this theory will be a defect CFT, or a DCFT. And so the goal of the talk today is to try to figure out what sort of DCFTs in various dimension can exist specifically in three-dimensional theory. So I'll make the setup a bit more concrete in a moment, but I'd like to motivate the idea first, if I can. So why should you care? And I'd like to offer two perspectives. The first is a sort of bulk perspective, that introducing this defect will give you access to new bulk observables. So you've broken the conformal symmetry. So you've no longer sort of protected yourself against the vanishing of, say, one-point functions, for instance. And this means you now get access to new correlation functions. For instance, the one-point function of bulk operators will no longer be zero. And importantly, this can be used to try to distinguish bulk universality classes that are very close together otherwise. So for instance, there's a well-studied case of the O3 CFT is very close to the cubic CFT. The scaling dimensions are almost identical. The spectrum is almost identical. But as we'll see, the defects that you can put inside of the O3 and cubic look very different. And so namely, they'll introduce different looking defect observables, and so it may be possible to sort of experimentally distinguish between these two close universality classes by examining their defects inside them. So that's a bulk perspective. But these are also CFTs in their own right. The theory that lives on the defect will still just be a p-dimensional CFT. And so doing this also gives us new universality classes. So it's interesting to try to study these as CFTs. They have some interesting features. For instance, the fact that you can embed them as a defect in a high dimensional space means they need to have a displacement operator. They can have tilt operators, for instance. So they behave slightly as a special class of CFTs. And there's been a lot of interest recently in studying the behavior and the properties of these DCFTs. For instance, their fusion. So if you take two of these defects and you bring them close together, so you separate them by some length L, and then you take a limit as L goes to 0. In the end, you'll find a single, generally what's expected to happen is you'll find a single defect in a different universality class, and there's been a lot of work trying to characterize these fusion rules. Similarly, there's been some recent success in trying to study these types of theories using techniques that have been developed by the CFT community, such as the bootstrap. Recently, it was figured out how to bootstrap lines using these defect changing operators. And so it's possible to use CFT techniques to get precision data. But to use these techniques, part of the problem that I want to address in the talk today is that they require some amount of pre-knowledge about what the theory looks like. So for instance, with the bootstrap, you want to put in gap assumptions to try to get rid of this continent, to zoom in on an island in order to really get precise information about what the CFT data looks like. And to motivate those gap assumptions, you need to know something about what the theory is before you're searching for it. And so while this is fine if you're looking into a well-studied theory. For instance, when they bootstrapped the magnetic line in the Ising model, but this has been studied for a few years. But if you instead want to ask what sort of DCFTs are out there, we need to look elsewhere for techniques general enough to search without these assumptions. And so this is the goal. The goal will be to classify all lines and surfaces in D equals 3. Now, there'll be some caveats. We'll be restricting ourselves to certain classes of theories, and we'll be working in perturbation theory, so we'll be classifying perturbatively accessible lines and surfaces. And the tool we will use that will allow us to look generally will be the epsilon expansion about D equals 4 minus epsilon. And here, this will allow us, as we'll see, to basically put in minimal assumptions about what type of defect we'll be looking for, and get find a class of solutions, find a wide class of solutions. Now, of course, the epsilon expansion, if you try to use it to compute CFT data, operator dimensions, OPE coefficients, bulk to defect OPE coefficients, it'll give you some asymptotic expansion, which may not be particularly accurate as you take some complicated epsilon goes to 1 limit. But nevertheless, it can give you approximate data, and more importantly, the epsilon expansion can tell you more rigorously about the existence of theories, the symmetry that those theories have, and perhaps most importantly, the OG stability of those theories. And this last one is most important for telling which types of defects could reasonably be realized in a laboratory setting without specific fine-tuning. So even though it's perturbative, there's some sort of maybe fuzziness about the results, there are some things that it can tell us, and these are exactly the sorts of things that we would want if we wanted targets for more precise methods like the bootstrap or the fuzzy sphere. Okay. So this is the goal. This is the tool that we're going to try to use to get there. But let me give you a bit of a map about how I want to use the tool. Yes, that's right. Or you can tell how many relevant deformations there are, how many irrelevant, and that sort of thing. Yes. So first, all defects come inside of some bulk. So before I can get to the defects, I have to tell you about what types of bulk we'll be looking at. Bulk, what classes of bulk theories. And then the goal will be to study lines. So here this is P equals 1, and surfaces, this is P equals 2 in 3 dimensions. But we'll start close to 4 dimensions, where we can also have interfaces, which are codimension 1, not fixed dimension, but fixed codimension. So we'll be interested in studying lines, surfaces, and interfaces, where P is equal to D minus 1. And so as you take epsilon to 1, this interface will then become a surface, but the type of interactions we can perturbatively place on the interface are different than from the surface. And then if I have time, I'd like to talk about some extensions of these fixed points into slightly more exotic setups. For instance, placing these inside of RG interfaces, where you don't just have one bulk, but you instead have 2, and also composite defects, which is similar in idea to the fusion of defects, this idea here, except the dimension of the objects you're fusing are different. So you're trying to fuse, say, a surface and a line. You can't get that won't look like just a surface or just a line. Instead, it will look like one of these composite defects where you have a line inside of a surface. So this is the... Do you have in mind this the story Andy had about the P equals 2 plus delta dimensional, transdimensional? Yeah, I think there they also, so there they were able to resum everything, and so to explain perhaps, you could also, another extension is to consider, as has been considered, is P equals 2 plus delta, where delta is a free parameter that doesn't depend on epsilon. And there they were able to continue both in epsilon and resum all the contributions in delta. And so they got, they can make predictions about P equals 2, they can make predictions about space filling deformations.
2 plus delta can be very large.
In the case that, what they were able to do was, I believe, yes, they could other people already did this. I won't be talking about this case. This is done in a paper by my advisor, Andy Sturgiu, Nadav Drucker, and Elia de Sabata from last year. I can't remember the archive number, but they... I believe that is yes. I believe that is the. I say believe because I cannot quite recall. I think I was not on this paper. From what I was told, they do resum in all delta, but I think there are caveats that delta has to be positive. But I think they can take delta large, but also not larger than the.
Small is not surprising. You say that for any variable, that means that delta can be arbitrary variable, can be arbitrary larger, and it's still varied. I will be surprised. Yeah.
Perhaps I don't want to comment too much on this paper, as I wasn't involved, and it won't be irrelevant. I think I think generally it's easier to always try to keep them either fixed dimension or fixed codimension, and things are much more straightforward when there's only one parameter to continue, I'd say. Okay, so before I can get to the defects themselves, let me try to briefly describe the bulks that we'll be working with. So we want perturbative control in 4 minus epsilon dimensions, and this severely limits the types of theories that we can look at, but thankfully it is a wide enough class of theories that it contains many interesting examples in 3 dimensions. For instance, well, I will get to that. So we'll focus on purely scalar theories. So we'll have some number n scalar fields. You can extend this as well to fermions, and in fact we do in the papers, but in the interest of time, I won't cover that. The extension is fairly straightforward when you can have Weyl fermions. And in order to be perturbative, the only sort of potential we can write down is some quartic potential. Where this lambda will obey its own beta function and lie at a fixed point. Now, there are a number of theories that are described in this way. The most famous one is the ON model, where you take this interaction to be ON invariant. It's just phi squared squared. And here, so here, lambda ijkl is epsilon over n plus 8 plus higher order terms times delta ij delta kl plus permutations. And this is a well-studied model in 3 dimensions. This has been isolated in the bootstrap, for instance, for n equals 1. This is the Ising model. But we can also take more interesting, perhaps, universality classes. For instance, there's also the hypercubic fixed point. Here, lambda ijkl looks like a rank 4 delta function, and this has the symmetry of the n-dimensional hypercube, z2 to the n symmetric product Sn. And it's here for n equals 3. This is the cubic model that's very close to O3 that I was talking about. And finally, the other model we will consider is the hypertetrahedral model, which is similar to the hypercubic, but now it has the symmetries of the hypertetrahedron, Z2 cross Sn plus 1. And you can write down an explicit form for this lambda tensor. It's much more complicated now. You have to write it in terms of the vectors that give the vertices of this hypertetrahedron. Its precise form won't be important. And I should mention that it's possible to do other ones. The sort of fixed points you get for the bulk have been studied by Hugh as well as others. And there are many more that exist. And indeed, in the papers, we also look at other fixed points by conical models. For instance, but in the interest of time, I'll focus on these because they already have the sort of salient features of the defect solutions that we find. Okay. So we want to insert some p-dimensional hyperplane into one of these bulks and add interactions on top of that. And the way that we're going to do this is we're going to take the action, the bulk action that we had before, and deform it by a term which only has support on this hyperplane. So we'll take the action and send it to S, it's S bulk, which contains this lambda term. And now some integral in p dimensions with some couplings times some operator, which is only placed on this hyperplane. And doing so, adding this coupling, will introduce new divergent diagrams, even to bulk correlation functions. But the essential point is that one finds that one can renormalize, and I can add purely defect counterterms, so counterterms of these defect couplings, and also renormalize the defect operators. And doing so will remove all types of divergences, divergences on the defect, and also divergences in the bulk. So the couplings HI will flow under RG, but these couplings lambda will stay the same. So the defect, the RG flow, once you introduce this defect, will be purely localized to the defect and will not affect the bulk operators in any way. Okay. And the counterterms for the couplings, I should say, can be found by renormalizing the bulk 1-point function of this operator. And the precise form of this operator depends on the dimension that you choose, because we want it to be the flows to be under perturbative control. So these couplings H can be only very slightly relevant. And so classically, this operator must have dimension P. And this very much limits the type of deformations that we can consider in this perturbative regime.
So A for UH is dimensionless.
No, it's classically dimensionless, but then when you go to in 4 dimensions, but then yes. Yeah, that's right. So we have the 3 cases: lines, surface, and interface. And what will these operators be in each case? So for the line, again, we're working in just scalar models, so we can construct these operators out of these scalar fields. P is 1, so we want an operator which is classically dimension 1, which is just the field itself. So this will just be d tau hi phi I. That's straightforward. And then this will make the bulk 1-point function of phi have divergences, namely this diagram where there's 1 bulk interaction and 3 defect interactions. This will be divergent, have a divergence, but you can absorb it in a purely defect counterterm and a counterterm for H. And at the end, once you do the calculation, you find that the beta function looks like this classical term minus epsilon over 2 hi plus a term that's lambda times h cubed. Okay, for the surface, we again want to find an operator of dimension 2. We just use 2 phis now. So the coupling has 2 indices. We now want to renormalize the 1-point function of phi squared. There will now be 2 diagrams, one that involves a lambda and a defect coupling, one that's purely defect. And in the end, one finds the beta function j plus with now a term that also depends only on this defect coupling, unlike the line case, and this will become important later on. And finally, in the case of the interface, we want a three-dimensional operator so we can just have 3 phi's. And you might ask why we don't sprinkle derivatives, transverse derivatives here to make up the dimension. You can in principle, but we want to, for the moment, just to consider deformations which sort of preserve the Lorentz symmetry. And you can't have like if you try to add something like 2 transverse derivatives on phi, you can use the bulk equation of motion to just relate this back to this cubic operator. So these really do give a sort of exhaustive list of the types of deformations we want to consider. And then here we will again get 2 diagrams, one with a single lambda and an h. And then one now with 3 defect couplings. Sorry, this is the bulk is in 4 minus epsilon, so this shouldn't be 3. This should be 3 minus epsilon. It's a codimension 1. Yes, yeah. But the continuation is the same. It's only 1 epsilon. You're not messing with the relative codimension. The codimension is fixed for the interface. That's the. No, sorry. Yes. In these indices? Yeah. Always the couplings have to be totally symmetric in their indices. Otherwise, it would. Here we always assume that it's completely symmetric. That's right. And so you do this calculation, you find that the beta function is equal to this. Where here the sum of perms is the sum of the the permutations of these ij and k indices, because you want the beta function to be symmetric in these indices, just like the coupling. And I should say as well, so this is just at 1 loop. Of course, more diagrams arise at 2 loops. And the beta function is known also at 2 loops. If I have time at the end, yeah. Yes. No, that's not. And yeah, we'll see how they modify. If I have time, we'll see how they modify the beta function. Yeah. So the surface is also known at 2 loops, and the interface is not, the beta function is not completely known at 2 loops. I think there are 3 diagrams which have not been computed. So it's this is only known to 1 loop. And if you want to include fermions, basically the only thing you have to do if you have Weyl fermions is to include the wave function renormalization term associated with phi. So it's very easy to include fermions, but I don't want to get distracted by that. I don't know. That's an interesting question. We didn't look into this. I don't. Yeah, I'm afraid I don't know. I'd have to think. I'd have to think more about that. The only constraint we'll demand is that it's real and symmetric. That's the only constraint we'll demand. Any other questions? Okay. So now we can. So the goal, as I said, is to classify these DCFTs, and so that becomes a question of classifying the fixed points of these beta functions, or alternatively just the roots of these polynomials. And then each one will be a DCFT, so if we can completely do that, we'll have our classification. So I'd like to spend most time talking about the case of lines, because here the classification we have is the most complete, and also because the sort of steps you do in each case are fairly similar. So I'll focus for a while on lines, and then I'll mention results for the surface and for the interface. So first, for lines, I'd like to briefly comment about the case when you take the bulk to be free. So here, lambda will be 0. There will be no bulk interaction. And you see that the beta function will just include the classical piece. And you can convince yourself that because this interaction is just linear in the field phi, even if you go to higher loop orders, there's no diagram you could construct that would be purely defect. They would always have to involve some lambdas. And so this is the beta function in general, which of course you see only has the trivial solution. And so we don't find any scalar line defects in the free theory. Of course, you can construct it if you try different constructions of line defects in the free theory. This may work. It's just this construction does not have any non-trivial defects in the free case.
Considering the infinite line, right?
Yes.
Do you have any trivial boundary conditions, infinite or just
No.
trivial boundary?
Trivial boundary conditions. Yes. Okay. So the next simplest case is the case where we take the bulk to be On. And this has actually already been studied fairly extensively. It goes by various names: the magnetic line defect, the pinning field defect, and so on. And this is the defect that was recently bootstrapped for n equals 1. And it's quite simple. The beta function you get once you plug in the fixed On fixed point value for lambda is at one loop, just epsilon over 2, it's 1 over epsilon over 2 h squared over n plus 8 times hi. And if you look at this, you can convince yourself that the only non-trivial solution is when this vanishes, or when the norm of this vector is equal to n plus 8. So there's a single fixed point, which just corresponds to picking some vector in your field space of some vector h. And this will break the On symmetry of the bulk to an On minus 1 symmetry on the defect. And the effect of this breaking is you see that it doesn't matter which direction we choose. And so we actually get a sphere of fixed points, which each describe the same physical theory. So they're all equivalent. And the sphere is, of course, just the orbit On minus 1. And it's possible to move along the sphere using these so-called tilt operators, which are the remnant of the broken, the generators that are broken on this defect. And so these are the tilt operators. They're very special. They have the protected dimension. Yes. And that's it's very, very simple case. That's sort of all I want to say.
That you won't have 1/8. Like you said, that the reason why that trivial is because in the interactions that you have in diagrams, there is only 1/8.
Here, for the free case, you mean?
Yes.
There it's trivial in the free case because for any diagram you write down that will contribute to the 1-point function of phi, it will always involve some lambdas. Because the interaction is linear in phi, there's no the only sort of purely defect diagram you could write down is something like this, but this won't contribute to the 1-point function, and so it will never appear in some of these connected diagrams. They'll always be proportional to lambda, and so when lambda is 0, they won't contribute anything. That makes sense. Okay, so the ON case is also fairly straightforward, I should say. So I want to talk about RG stability. I should say that this point is RG stable. So there exist no relevant operators at this for this defect, which was confirmed by the anomalous dimension is always positive, so it's always always irrelevant. That's right. But the statement about stability isn't so interesting because there's only one fixed point, so there's not much to flow to or from. And so more interesting will be the case when we take the bulk theory to have some finite group for its symmetries. So that's what I would like to focus on. So there were two other bulks that I highlighted, the hypercubic bulk and the hypertetrahedral. For the hypercubic, recall that it had symmetry group Z2 to the n, semi-direct product S. N. The expression for lambda can be found in various places in the literature. One finds after plugging it in, you get a similar beta function to the ON, but with some crucial differences, 1 minus. So there's also a term that goes like h squared, but now, because you have this symmetry under sort of permutations of these indices, but not the full ON symmetry, we can have a term that looks like just hi squared. And so staring at this long enough, you can possibly convince yourself that all fixed points fall into any plus 1 equivalence classes of the generic type. So we'll have some vector. This will just be some representative. The first n, say, will be non-zero. And then the last n minus n will be 0. And you can think of these vectors as lying at one of the centers of one of the sort of hyper edges of the cube. So for instance, for n equals 3, it's easier to visualize things because there the hypercube is just a cube. So if we take little n is equal to 1, so if we take little n equals 1, we only have one non-zero component. You'll see it just points to the center of a face. If we take n equals 2, it'll point to the center of an edge. That's right. Because the sort of group acts by a field redefinition, and so they'll have they're the same up to a field redefinition, so they're the same physical point. But they will break this group. And then finally, for n equals 3, it will just point towards one of the vertices. And so you can see how based on the form of this, how it will break the group. Whenever you've turned on one of these couplings, you'll have an explicit phi now in the action, and so that'll break the Z2. But because they're all the same, there'll be some Sn remaining symmetry where you can permute these. And here, because the couplings are 0, the Z2 remains. So now there's some smaller hypercubic group. So some Z2 to the n minus n semi-direct product Sn minus n. And for n equals 3, this becomes the group D4. Then for this becomes the group Z2 squared. And finally, this is the group S3. And so you can see already that this is very different from the case of the ON model, which is part of the benefit of using these defects. There for O3, if we wanted to look at the difference between the cubic and the O3 universality classes, there was a single universality class. Now there's multiple, and there can be non-trivial RG flows in between these different defect classes. And you can ask, what are the stability properties? And one finds that for n bigger than or equal to 4, the most stable point will be the one where we turn on all of the couplings. So this will be the sort of the vertices. But then for n less than 4, the most stable one will be the one where we only turn one of them on. So there's a sort of the faces. But in either case, I'd like to highlight for the next bulk that the stable fixed point is unique for any particular value of n that you choose. So here we see we have n equals 3, so the D4 fixed point will be the stable one. Okay. Now finally, I'd like to turn to the last bulk I want to talk about, which is the hypertetrahedral. And here we'll see there's a much richer structure of RG flows than in either the cubic or the ON case. I should say you'll still get so in the ON case, we had this sphere of fixed points that was you obtained by the breaking of ON to ON minus 1. So similarly, it won't be a continuous manifold because the original bulk symmetry group is finite, but you'll get just a set of equivalent points. So the center of any face will be the sort of set of n equals 1 fixed points. The center of any edge will be the set of n equals 2. And so on. So you still get a set of points, but there's no longer tilt operators because you haven't broken any continuous bulk symmetry. Finite, and generally small. But we don't assume any particular limit. But if we're looking explicitly, then it'll be for n equals 1 or 2 or 3 or something like this. Okay. Yes, that's right. Yeah, because this group, it can sort of do a parity along one of the axes, or it can permute the edges of the cube. And you can see that, the points won't be invariant because you see this, if you say do parity in like the x direction, this face gets mapped to this point. So it's not invariant, but the class, the orbit, it'll form an orbit under this group. So you can, there exists a group action which can bring this face to any of the other faces, and so it's an orbit. That's the invariant statement, that it points towards a face. This has 8 generators. This has, no, 8 elements, sorry, 8 elements. This has 2, yeah. 4 generators. Yes, yeah. 2 and then 2 as well. Yes.
My question is, like, is the most stable one special somehow?
No, I don't believe so, because you'll see the stability changes for n equals 4. So if we were looking at this, say for one higher for n equals 4, we'd find the stable point would be the one with S4 symmetry, not a. This is just for one loop results, but the stability properties are expected to hold. In principle, yes, but I mean we expect the stability properties generally to not be significantly changed by higher loop calculations. Okay, so here the symmetry was Z2 plus Sn plus 1. And it's easiest to realize this symmetry not on the phi i's, but instead on these vectors phi alpha, which you define to be a contraction of alpha with these ei's, where these ei's give the vertices of the hypertetrahedron. So alpha equals 1 to n plus 1. And then what one finds after doing some work, the beta function is much more complicated, so I won't write it down, but you can write it down in terms of these E vectors. In the end, one finds 3 sort of families of equivalence classes. There's one family with Sm cross Sn plus 1 minus m symmetry, where m is an integer less than or equal to n plus 1 over 2. There's then also a family with Sm squared times Sm n plus 1 minus 2m, where again m is less than or equal to n plus 1 over 2. And then there's finally a different family with symmetry Sm, m prime cross Sn plus 1 minus m prime, where m prime is also less than or equal to n plus 1 over 2. So there are many more fixed points. But the most interesting fact is that when you look at the stability, you find that these 2 classes are always unstable. But if you look at this class of fixed points, you find that it's stable as long as 3m is strictly bigger than n plus 1. And so you see now that there can be multiple stable fixed points, because there can be multiple values of m if n is large enough such that m is less than or equal to n plus 1 over 2, and that 3m is bigger than n plus 1. And in general, there will be floor n plus 1 over 2 minus floor n plus 1 over 3 stable fixed points. which are simultaneously stable. And the first n at which this begins to be bigger than 1 is n equals 7. It's 2 for n equals 7, then it's 1 again for n equals 8, then it's 2 again for n equals 9, and then it becomes higher. So n equals 7 and 9 and higher are then interesting. And the point is that because they're all stable, this means that there can't be RG flows in between them. And so if you're looking at the sort of the space of theories, there'll be some stability domains where all of the RG flows here flow to one DCFT. And there'll be a different separate domain where all of the RG flows flow to a different DCFT. But these domains can't speak to each other. And this is very different from what happens in the other bulk, for other bulks. In fact, the hypertetrahedral is the only one that we've observed that this multiple stable fixed points can happen. It's very different from what happens in the other types of defects, surfaces, and lines, and it's very different from the bulk theories as well, which is what makes this hypertetrahedral class of theories interesting to study the presence of these multiple stable fixed points. Yeah, that I'm afraid I don't know. I'm afraid I don't know. I mean, there will be other fixed points in these other unstable classes that lie in these domains as well. I don't know if they can be nicely grouped in some group theoretic way. It's not clear. It's not clear to me, I'm afraid. You flow to one of these two. So they're all stable against perturbations towards the trivial defect, but then you can perturb towards one of these stable defects and they'll just flow. There's some relevant operator. So for that, I think, so m has to be less than or equal to 4, and 3m has to be bigger than 8. So for n equals 7, I think it's m equals 3 and 4 will work. So that'll be some, it'll be some S3 times S5 and some S4 times S4. Yeah, no, it grows sort of linearly in n. I mean, it's a floor function, so it sort of makes steps, but it's generally linear. Yeah, so it becomes quite large. Yeah, these groups are all these permutation groups. This Z2, when you represent the bulk symmetry in this way, always acts just by sending all the phi i's to minus themselves, and so this is always broken by a non-trivial line defect, and then you simply you construct these by privileging certain E vectors, basically, which breaks the remaining symmetry group. S4 squared, yeah. All of these are unitary fixed points, that's right, they're all real. Yes, we didn't study the particular number because we weren't as interested in them, but you can find non-unitary fixed points, especially in the interface case, but for lines as well. Yes. Okay, I don't have much time, so I'll be very brief about surfaces and interfaces. I do. That's right. It's until 3. Okay. Then I can go a bit more slowly. But the story is basically the same. So we had the beta function. I'll write it down again. And the goal is to simply solve this, to see if we can solve this by plugging in the different values for the bulk lambda and trying to exhaustively classify the fixed points. And that will give us the DCFTs. I should say that the classification wasn't done by us, but for completeness, I'll include it. It was done in this nice paper, 25.3.05519 by Andrei Anachichuk. And Sabine Herbe. And so I'd again like to start with the free theory. Here, the difference, we see already a difference with the line case. There is this self-interaction, just this purely defect term, and this is what allows us to get non-trivial surfaces in this way. We just set lambda to 0, and you can see that this is just sort of a matrix equation setting the eigenvalues of this matrix H to either be epsilon or 0. So the fixed point will always take the form where we put a certain number of epsilons along the diagonal. We can choose, say, n of them, and then the rest are 0. And this will break the bulk ON symmetry to ON cross O n minus n. And the stable fixed point is always the one where we turn on all of the couplings. So it's just Hij is just proportional to the Kronecker delta. And this is the only one. It's very simple. Yes. And I should say, there are no, this is the only defect, purely defect term. You can compute the other diagrams. All the diagrams will look sort of like this. If it's pure defect, there'll be n jumps. And you can compute this diagram analytically for any number of jumps, and you find that if n is bigger than 1, there's no 1 over epsilon pole, so it doesn't contribute to the beta function. So this is a 1 loop exact result. But there'll be more terms when we high loop order terms when we turn on lambda. Okay, for the ON, we find something basically very similar. It's not such a simple form, but the only fixed point I find is you turn on n diagonal entries and break the bulk symmetry group to On times little n times O big N minus little n. So n is less than or equal to n. But now the stability is a bit more interesting. For n less than or equal to 6, again, the stability preserving defect is stable. And then for n bigger than 6, there is actually no stable fixed point. This n equals n is unstable with respect to deformations towards n equals n minus 1. But this point is also unstable. So for every fixed point, there will always be at least one relevant operator that you can use to induce in RG flow. And I should say that here, the symmetry preserving defect is often called the ordinary surface defect. And has been studied fairly extensively, for instance, in this paper where it was found that it sort of factorizes space into two ordinary boundary conditions. But that is just a comment. Okay, now something that was used to get this classification was the fact that because there's ON symmetry, you can always diagonalize this matrix, and so you don't have to care about the off-diagonal terms. Now for the other bulks, this is no longer true, and in principle, and in fact in general, you will get fixed points which have off-diagonal terms. However, it's much harder to handle them analytically, and so in the classification, focus analytically on the case where Hij is diagonal, and then you can try to numerically solve the beta function explicitly for low values of n to see how many non-diagonal points there are. So for hypercubic, for the diagonal points, it's a very similar story. Again, basically you pick n of them to be the same, and you break the hypercubic group into two. So sum z2, the n, my direct product Sn, and this z2, the n minus n, my direct product. It's n minus n. And again, the exact same stability property holds. That for n less than or equal to 6, the stability, the symmetry preserving defect is stable. But then for n bigger than 6, it's unstable with respect to deformations towards this defect. Okay. And finally, the hypertetrahedral case. Here, actually, even though for the line defect, the hypertetrahedral was the hardest case to do because of the sort of nasty form of the bulk tensor, actually for the surface, when you assume this diagonal form for the coupling, it becomes the easiest case, and there are only 3 fixed points for any n. There is a symmetry preserving fixed point with Z2 cross Sn plus 1. And then there are two Z2 cross Sn fixed points. And here, this is always the stable point. But this is just for the diagonal. Both of these results are just when you assume a diagonal form, to give you a sense of how many non-diagonal fixed points there are for the hypercubic case. So you can always just try to numerically find solutions to the beta function vanishing. So for n equals 2, there is 1, and then this increases dramatically such that by n equals 5, there are 21. And for the hypertetrahedral, for n equals 5, there are, I believe, if I recall correctly, 29. I do not have it in my notes, but I believe it's 29. So you see that as n increases, the number of non-diagonal points begin to rapidly, they become much more prevalent than the diagonal points. However, these are always unstable. in all of the examples found numerically, these are always unstable towards the diagonal points. So they're less interesting. Okay. That's all I want to say about surfaces. If there are any questions. This was 2 loops. Yes, this is 2 loops. That's right. So finally, I can get to the last case, which is interfaces. And this is just 1 loop. This is only the 1 loop beta function is known. So less can be said. Which numbers? The symmetry breaking or the? No, these always stay the same. Going. There are certain cases. Okay, there are certain cases where operators appear to be marginal at 1 loop, but then get corrected at 2 loops or high loops. But then they generally they become irrelevant. Generally. No, that has more to do with sort of the fact about the bulk tensor, just based on the form. So the bulk tensor has some n dependence, and n equals 6 is a sort of special case for that. Yeah, that doesn't change it. High loops. Okay. So now the last stop on the census, interfaces. Let me write down the beta function again. So there's classical piece again. There's a self-interaction term. And then there's a in bulk term. And so here, I should say that the fact that the coupling now has many more components makes it much harder to deal with this analytically, and especially this minus sign here means that there aren't a lot of unitary solutions. You find a lot more imaginary solutions because of this minus sign. And so most of the work that was done with interfaces, we did numerically to try to identify fixed points for low values of n. But there is some analytic work that can be done. So if you have a group G, which has some rank 3 invariant tensor, D, then you can show that by taking H to be some multiple of this tensor, you can get some fixed point if you know some of the properties of this tensor, such as its traces or how what its product looks like. And this way we find a few unitary fixed points analytically. So for n equals 5, there is an SO3 fixed point. For n equals 8, there's an SU2 fixed point. For n equals 14, there's an SP6 fixed point. And then for n equals 26, there is an F4 fixed point. And these exist both in the free bulk and in the ON bulk. And in the ON bulk specifically, there is also, for n equals 3, an S4 fixed point. I should say that fixed points with these symmetries exist for different values of n. It's only for these values that they become unitary. For the others, they become imaginary. And these one can check. These are always stable with respect to the trivial defect. However, there always still exists at least a symmetry breaking relevant deformation that one can do. Okay. So these are essentially the only fixed points we can find analytically. Otherwise, we must work numerically. To give you a sort of sense of the scale of the space of theories, I'll write down some of the numbers of fixed points that we find. So because there are more components, we find many more fixed points than in the line and the surface case. And we also find many more symmetry breaking patterns. So for instance, if we choose an O3 bulk, so for n equals 3, we can get O2 interfaces, S4 interfaces, S3 interfaces, Z2 squared. If we choose the cubic, again for n equals 3, there's D4, there's S4, there's S3, Z2 squared, Z2, and even some interfaces which have no symmetry remaining whatsoever. The H completely breaks the cubic symmetry. And the symmetry breaking patterns simply increase as you increase the number n. So for instance, in the free bulk, we find that there are no fixed points, unitary fixed points until n equals 3, and then there's 1, 5, 18, so on. And this can be traced to the minus sign in front of the purely defect term. There exist non-unitary fixed points here, but it's not until n equals 3 that you can conspire, cook up some h to make this minus sign go away, essentially. For on, there is a fixed point at n equals 1, and it increases. For n equals 4, there's a problem with the numerics. There is a rank 3 traceless symmetric cubic operator in On, which happens to have anomalous dimension exactly equal to epsilon over 2 at one loop, which cancels the classical term, and so it appears at one loop it looks like you're getting some sort of exactly marginal operator, but this of course isn't true. There's some epsilon squared anomalous dimension here, and then you have to go to 2-loop to find fixed points, but because we don't have access to the 2-loop beta function, the complete 2-loop beta function, we can't do that. So we're not sure what the fixed points are here. There's a similar problem in the cubic case, but that's only specifically for this n equals 4. For other n, it's fine. That's 1, 2, 26. And then for the hypertetrahedral, it's 1, 3, 26, 169, and so on. So you see the rate of fixed point, the number of fixed points increases very, very quickly. That's what I want to highlight. Are there any? No, this is the G on the defect. So this has to be a subgroup of the bulk symmetry. So namely, it has to be a subgroup of On. And if you're looking at cubic, it would have to be a subgroup of the cubic group. It's the G that's left, that's right. So on this, for n equals 26, there will be an interface with F4 symmetry remaining out of the ON symmetry, and everything else will be broken. Yeah, we tried to do some numerology, but we weren't able to do it.
Two of those numbers, there's 3 times 1, 2, 4, and 8, which related to real complex quaternions and octonions.
Okay, so I'd like to briefly touch on some extensions of this idea, specifically on the idea of RG interfaces and how you can put defects inside of them. So the setup before was we just had a single bulk with some couplings lambda, and we put some defect in here. But now what happens if we instead study the case where there are two CFTs, one on either side, and so they'll be separated by some interface called the RG interface. And we instead place the defect within that interface, so it feels the effect of both bulks without being in one. This type of RG interface setup has been extensively studied in 2 dimensions, where you can use the folding trick to map it to a conformal boundary. And it's also been studied to a certain extent in higher dimensions, but generally one of the CFTs has been taken to be free. But in principle, you don't need to do that. You can have them both be interacting and have lambda non-zero. And what happens? So now we again want to start with a bulk action of n scalar fields. And now we have 2 terms in the interaction, one for positive z, one for negative z, maybe some lambda 1. One for lambda 2. And we again want to perturb by this defect action, but now we want to put it specifically at z equals 0 so that it's within the RG interface. If you put it on either side, you can do this, but what you find is that the counterterms are exactly the same as if it was only in this one bulk. It doesn't feel the presence of the bulk on the other side of the interface. So you really need to put it in the interface to get something new. And so, for instance, in the case of the line, before we had a single in the multiscalar case, these are always can be connected by an RG flow. So yeah, in this case, they always will be. So that's the same idea. Yes. So before we had a single diagram with 1 lambda in the bulk attached to 3 in defect interactions on the line, but now we have 2 diagrams because this bulk insertion can either be on the left or on the right, depending on if it's CFT1 or CFT2. So here there'll be some lambda 1, and there will also be some lambda 2. And here the integral over this point will only be over half space. Now you can do these integrals and you can find what the 1-point function of phi is, and in the end you find that at 1 loop the resulting beta function for the coupling is what you would get if you replaced the lambda we had before by just the average of these two. So lambda 1 plus lambda 2 over 2. And at one loop, this makes sense. There was a single lambda. Whatever we get here has to reproduce the result we had before if we set lambda 1 equal to lambda 2. And it has to be symmetric, so it can only depend on their sum. So it has to just depend on the average. For higher dimensions, and indeed for different quantities, like if you compute the free energy of this interface setup, as soon as there's more than one lambda, it doesn't have to depend just on the average anymore, and it can, in principle, become much more complicated. But at one loop, for all of the beta functions, there's only one lambda, so they'll only depend on the average. And because higher loop order corrections to the fixed points are fixed by linear equations from the one loop fixed points, there's still a sense in which you can view these lines as fixed points living in an averaged bulk. And so what's important about this is that the type of symmetry groups you can get for these lambda tensors are very specific. There's specific subgroups of ON. And so there aren't necessarily that many choices of bulks you can put the line defect in. But now the average of these two doesn't have to have the same symmetry at all. It in principle can have a much, much smaller symmetry. So for instance, if you choose n equals 5, and you choose lambda 1 to be hypercubic at a specific hypercubic point, and lambda 2 to be at a specific hypertetrahedral point, the only symmetry that lambda 1 plus lambda 2 has is just Z2 squared, which is a much smaller group than you could realize defects living in beforehand. And this means that you get a much richer spectrum of defects. You can imagine that the symmetry essentially relates families of solutions that wouldn't be related if the symmetry wasn't there. And so when the symmetry is smaller, these solutions break out into their own individual fixed points. So if you if you make a plot, so you have, say you plot the value of h squared, the norm of the vector, here you put this hypertetrahedral point. So if the bulk is purely hypertetrahedral, you get, I believe, some 5 fixed points. If the bulk is purely hypercubic, you would again get some 5 different fixed points. But then if the bulk is the average of the two, as it looks like in this RG interface setup, you find about 70 fixed points broken up into innumerable families. And these fixed points have much less symmetry than we saw in the lines before. They, in general, either have Z2 symmetry or no symmetry. And it's also a way of generating many more stable fixed points. So here, in the for n equals 5, there's one stable fixed point in both the hypertetrahedral and the hypercubic case. But you can see this one fixed point is breaking up into, I believe it's 7 stable fixed points, which then sort of recombine at the hypercubic point under the hypercubic symmetry. But they're all, in the RG interface, they're all RG stable. So one also expects many more stable fixed points.
Any question?
Yes.
But do you have dynamic or
No. No. That's right. These, you mean? That's an interesting question. In that case, you would be essentially embedding the line into a boundary, so it would be a composite defect. Presumably the answer is yes, that it should be the case. We haven't looked into this. We haven't studied the composite defects of lines with boundaries, but it should be possible. Yes, it should be possible. I guess the perhaps more interesting case is when you say you don't add a line, but instead, so this is already an interface, you add the cubic couplings that we had before along the entirety of the interface. So you have some cubic interaction added to this RG interface. You can again find fixed points. It's the beta function. You get more diagrams. You can do the calculation. It essentially just replaces lambda by the average at one loop. And this fixed points in this setup should just be boundary fixed points for twice the number of fields for some direct sum bulk. But this one-to-one correspondence we haven't understood yet, but it should be there, yeah. Okay. So I think I should wrap up. All I want to say in the outlook is that so clearly there exists a very wide space of theories of these DCFTs that one could study. And I think now that we have access to some predictions about them perturbatively, it would be interesting to try to isolate them non-perturbatively. Say the bootstrap. Specifically for the lines, because this recent bootstrap work was done with these defect changing operators, it should be possible to find all of the lines that we find after some work with the bootstrap. And an interesting question is if you can find, so you can see that if you take n equals 1 to be free, 1 to be Ising, you should also get a non-trivial line which looks slightly different from the Ising magnetic line defect. And in that paper when they bootstrapped this magnetic line, the assumptions they made about the bulk spectrum threw away this RG interface, this line in the RG interface setup. But by choosing different gap assumptions, it should be possible to isolate it and demonstrate.
You start from some common bulk, I guess, with zero coupling, and then you flow on half the space in one theory, half the space on another. It's not
Yeah.
necessarily there's a flow from CFT1 to CFT2, I guess. There's just a joint parent where you integrate different relevant deformations of both half space.
That's true. That's the sort of practical way that we do the calculations. But I think in principle, it would also be possible to do some conformal perturbation theory where you start with, say, CFT1 has some relevant deformation to CFT2, and then only integrate that relevant deformation on half.
For example, you just take just something stupid like lambda 1, IJKL all equal 1, say, and everything else 0, and then lambda 2, IJKL equals 2, and everything else 0, then I guess there's no flow from one to the other.
But those aren't necessarily fixed points. They're always there's a theorem by Michel which you can show using this theorem that for any fixed points of the beta function, you can always find a flow that exists between them. Yeah, there's always a relevant deformation from one to the other, depending on which minimizes the A function. And so for this case, I think because that's true, I think these two pictures are.
Maybe that's not interesting.
Lambdas are always at some fixed point for the beta. They're not arbitrary lambdas.
Yeah, but I mean, I'm asking, like, is his definition of CFT interface or RG interface that you start from a common bulk with just whatever. In the case, the parent theory is just a free theory, and then you perturb differently on the two half spaces, or do you start from some CFT and then you do it? If you do that, I would imagine there's a condition on lambda 1 and lambda 2. Maybe A1 has to be greater than A2 without loss of generality the other way around, right? If A1 is equal to A2, I mean, here would sort of forbid how much upflow you can do.
One can always be the UV, one can always be the IR.
Yeah, I think so. An example of this is if you pick two CFTs from the same universality, ON universality class, and there the A will be the same because it's an ON invariant, but then lambda 1 and lambda 2 can be different. And yeah, I guess I wouldn't know how to handle this. It's sort of like on half space you'd be performing an ON rotation, but only on half space. Yeah, I guess the picture we have of an RG interface is from this setup, which can handle such cases. But I don't know if you would call them an RG interface or if there's something better. Yeah. Yeah.
Yeah, you can have like A1 equals A2, and then it's not RG interface. I mean, it's not a word, it's just like a different setup, I guess, and there's not a deformation from CFT1 to CFT2. There could be a marginal deformation, yeah. So maybe that's what we, right? I guess it's by a tilt in that case, right? The example I gave is probably by a tilt. That's right.
Yeah, yeah. Okay, so there's targets for the bootstrap, and then also in the study of DCFTs, these fixed points provide sort of more interesting examples as a sort of playground for studying the properties of these DCFTs more generally. So for instance, for defect fusion, it's been known that in the ON case, if you try to fuse a vector H with a vector H prime, then the result in the IR is just the average, suitably normalized, of H and H prime. So it's a very simple fusion rule. But this is really because there's only one type of fixed point and it's stable. But for instance, in the case of the cubic, there are multiple fixed points, and so you could try fusing different classes of fixed points, and we expect the fusion rules to be more interesting. And for the hypertetrahedral case, because there are multiple stable fixed points, it's possible that you could even get a sum here, that it could be much richer fusion. And another interesting thing which we're studying at the moment is not fusion, but composition. Where you don't try to fuse defects of the same dimension, but you instead say, take a surface and you take a line very close together, and in the end, the object you get shouldn't be one or the other, but it should be instead some composite defect of a different new universality class. Okay, I think that's all I want to say. Thank you.
So you mentioned at some point that if you include a group of corrections to the analysis, it's going to change regarding the stability.
That's right.
What is that? Because, I mean, you can look at actual, say, static actual. In principle, there are cases where fixed points become Landau poles or vice versa.
So if you go to large order, of course it makes sense because it's not convergent.
Yeah, I think it's certainly for epsilon small, the higher order questions will be suppressed relative to the one loop results, and so they'll be yeah. Right, but as you take epsilon to 1, the question, I guess, is are you secure And there, I think it's more expected, I guess, as the epsilon will be some parameter in your dynamical system, and the solutions to dynamical systems are generally fairly simple. Like not much can happen necessarily as you change these parameters, and so we expect the broad strokes properties of these fixed points, like stability, like their existence, to stay the same. Of course, this could change in extraordinary cases, so it is very useful to try to use more non-perturbative techniques like the bootstrap to actually demonstrate that rigorously that these do have no relevant deformations, but that's the expectation. Well, again, yeah, there are specific examples, but it's not expected to be a general feature of these fixed points. So perhaps in a few cases that is true, but generally these fixed points should survive to 4 dimensions fairly unscathed.